Okay. So just to review, in case you're looking at this 6 months later, we observed the rotating beam. And I'll put the camera on the beam here shortly, but we observed the rotating beam. And I used a pendulum. And for the record, I don't know how long the pendulum is because I think my meter sticks are packed up. Actually, I'm pretty sure I have them because they're too long to pack. So I'll be able to find them as soon as I realize I need them. So I can measure the length of the pendulum, and that's another thing, because the length of the pendulum determines how long it is between swings. Okay, but every time the pendulum completes, the pendulum's about, I'd say, 2.5 feet long. Okay, I think it's less than a meter. It's maybe getting closer to 3 feet, almost a meter. If it was a meter, then very nearly, sorry, zoom. No, it's not zoom. I don't know what it is. But first time you record, zooms back. You see more of me than I could see of the board. Nobody wants that. Okay. Again, if the pendulum is a meter long, then it's just about 2 seconds between cycles. So it'd be half a second between half cycles. Okay. It would pass the center point every second. Very nearly. And there's a formula for that, which I'll probably give you, but then we'll derive it. All you need is a little calculus. Okay. So anyhow, from the length of the pendulum, we can determine how long it is between the tick marks. So actually, I did a table of the number of ticks versus time, but then I graphed actually, the number of ticks versus the time, okay? And actually kind of said this backwards, we're not going to worry about it. Now, to make that graph, after 2 ticks, we'll say the time was 2. It might have been closer to 3, but we're going to say 2 because ultimately it's not going to make a big difference. Okay, so we just count the tick before the check mark. The check mark is when the thing has completed a revolution. Okay, then there's 3 more ticks before the next revolution is completed. So I could put my numbers 2, 3, 4, 3. Start with 2 and then put a 3 here, 4, 3. Next one is 5, 5, 6. 5, 5, 6. And I can determine then the time between ticks, time as measured in ticks of a pendulum of unknown length. But if we don't mess with it before I find the meter stick, we can write down the length. So we could actually then do this in terms of seconds. Okay, right now, this is in terms of pendulum periods, and this is in revolutions. Now we can interpret this string into a table, then into a graph. And as I said, we're going to do one where you might have 30 or 40 revolutions. And we're going to do a few of these. And what you then want to do is one way or another, put the thing in, do a hand sketch graph. If there are 40 revolutions, maybe you only count every 4th revolution, so you've only got 10 points to plot. But put all your data into Excel. It doesn't take long. And then make a graph and do a curve fit with a trend line. You know how to do that? If you don't, we'll turn my computer around, you can look over my shoulder, I'll just bring it out there. It's really easy. Really, 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 really easy. Now, Excel has probably changed since the last time I did it, so I won't be able to figure it out. You know, they move things around, but it's one of the primary things, so you just got to use a little common sense. And you can do a trend line, it'll give you a formula for the curve. Okay. Now, once you have a formula for the curve, then what you have is a graph of theta of t versus t, where theta is your angle. You measure angle in revolutions. You measure an angle in degrees, you can measure it in grads. You can measure it in different units that are interconvertible. Okay, convert revolution to degrees, you just multiply by 360, right? 360 degrees per revolution, or 2 pi radians per revolution. And we're generally going to use radians because it's the most convenient unit, even though you're probably less familiar with it than you are degrees. If you do it in degrees, you can still convert it to radians. Everything you calculate based on degrees, you just change your units and you get radians. And your time in seconds, you get this curve. Now, what's happening to the slopes? The slopes are decreasing, right? What does the slope of this curve represent? Well, it represents a rate of change of theta with respect to t. Now, stop the video for just a second. If I can find the button. There we go. Okay, so I got a good answer. The slopes of this thing indicate angular velocities, rates of change of angular position. Okay, so slopes are still visible here. You have rates of change. Angular position. Be specific with respect to time. I.e. the derivative d theta dt. Now that's angular velocity. So if you put this information into Excel and get the function, you can take its derivative. You're going to choose, you're not going to choose to do a quadratic function. A polynomial of degree 2 would be a quadratic function because the second derivative of any quadratic function is what? What can you say about the second derivative? It's constant. You got at squared plus bt plus c. You take the second derivative, and it's going to be 2a, right? And the derivative of t squared is 2t, right? And the derivative of that is 2. And the second derivative of everything else is going to be 0. Second derivative of t, first derivative of t is constant, second derivative of t is 0. And the first derivative of the constant term is 0. So you choose a third degree polynomial, which will show you if there's some nonlinearity in the velocity graph. Okay? So, and I'll give you specific instructions on this, but your theta of t is going to be a cubic function. Ideally, it's quadratic. Because the second derivative of quadratic is constant. In the second derivative, well, what's the second derivative represent? Let me pause.